Okay, here we go. We got a lovely orange car, masterfully drawn, I might add. Moves to the left at 4 meters per second.
Cool story, bro.
Thanks, Billy. Okay, so we got a little scene here. Let's add a car. There it is. And let's, what do we got to do? Let's get that car moving now. Let's match that beautiful story that Bill just loved. Me and Bill, you know, we hang out. Anyway, so let's add a little bit more to it so it can actually be a problem instead of just a story. So we're looking for something. We're looking for how far apart the tree is. So we have a couple of pieces of information here. We have 4 meters per second. That's going to be the speed. Now, it does say to the left, so we're kind of separating those things out here. We might see things like that. And we have a time, 2 seconds, no direction there. So we have 4 meters per second and 2 seconds. And it just says how far apart are the trees. So that's not specifically asking for a displacement. So I'm not going to worry about direction here. Even though it does say it's going to the left, it's just asking how far apart they are. So the fact that it's going to the left doesn't really matter. But we can figure out how far apart the trees are because we know how fast it's traveling and how long it takes to get from one tree to the next. So we write down what we are given, and we can figure out an equation to use. Right? Really, we're just looking at something simple here. It's v equals d over t. And substitute in. You notice I'm including units here. That is a requirement for us in order to get full credit on this stuff. So, you know, we multiply, cross multiply, however you want to think about it, and we get 8 meters as the seconds in the denominator cancel out. All right, so slightly different question. Now we are asking for the acceleration. Now the acceleration is a vector quantity. All right, so we are going to care about direction in this case. We'll get to that though. All right, so same initial thing, and this time we're saying it slows down and comes to rest 2 seconds later. What is the acceleration in the car? Okay, now that comes to rest is important. It is a hidden thing in there. It is a hidden velocity that you might miss. All right, and we are looking for the acceleration. So I'll put that in red. All right, so let's take a look at the equations that we have here. We have v equals d over t. We have the acceleration is a delta v over t, so that's a change in velocity over time. So that's a v final minus a v initial, and that change is going to happen over a period of time. We can reorganize that equation to look just like vf is equal to vi plus at. We have vf squared is equal to vi squared plus 2ad. That's another equation. And we have d equals vit plus 1/2 at squared. Each one of these are just equations that we can use to describe motion, to figure something out about how something is moving. You know, the only difference between when we use one versus the other is really comes down to what information we're given. There's no magic other than that. So good bookkeeping is going to be the way you know which equation you need to use. So these are what's known as the big five. All right, I can write them down right here. Normally when we're doing these problems, we're going to say, you know, which equation do I use? We're going to use our reference table. In this case, I just have them written down right here in order to help us determine. A really good strategy to help you determine which equation to use is to write down your unknowns and write down your givens so that you can then associate numbers with it, and then you can say which equation has all these variables in it. Okay, so we have immediately a speed, and that speed is 4 meters per second. So then we say it slows down. Okay, yeah, we're underlying that, and we have a time. So we know it's slowing down, and we know we have a time. So right now, we only really have 2 numbers here in order to find this acceleration. Okay, when we look at these equations, that's not going to be enough information, all right? We might initially say, like, well, don't I have enough information to solve for the distance? No, you can't use that one because if you are looking for an acceleration, and whenever an object is accelerating, you must use an acceleration. So that equation's got to go, okay? We don't have a distance, so we can't use this equation. We don't have a distance, so we can't use this equation. Both these equations got to go. All right, so we're left with these 2 equations. And if you remember from before, these 2 are really just the same thing written in a different way. So, you know, I think the second option is the happier option. I don't know, there was a smiley face there. But I think the second option it expresses everything out so you can see exactly where they are. But we don't have a v final, right? Just kidding. Yes, we do. It says it comes to rest. So because it comes to rest, that means we know that final velocity. it stops. So the final velocity is equal to 0. Let me just write that in there. That means that 4 meters per second is the initial velocity. It starts at 4 meters per second and it ends up with 0 meters per second. It stops. There's our v final. So now you can see that we have 4 variables written here, right? VI, VF, A, and T. Now, we can also look over to the left and say, look, we have VF, VI, VA, or A, and T. So that's going to be kind of what's going to key us in. There's no magic to knowing which equation to use. All right, so now that I've written down everything, I can write down my equation again, right, because we're pretending that orange stuff is coming from the reference table. Now, it says it's going to the left, and we're looking for an acceleration. Direction is going to matter here, okay? And if we're going to stick with that standard notation, that standard, everything to the left is negative and everything to the right is positive, then we should just stick with that all the time, at least for now. So we're going to call that a negative 4 meters per second. So now we can solve for acceleration, and then when we get our acceleration, whatever direction it has on it is going to tell us whatever direction that acceleration is going. So substituting in, making sure to be careful of that negative sign there, solving this, you doing your algebra. Remember, we added the 4 to the other side, so that negative drops off, and we get 2. And it's meters per second divided by seconds, so we call that meters per second squared, or meters per second per second. But how come it's positive, right? And what does that actually mean? So in order to figure this out, it's helpful to look at a picture. And, oh, there we go, that beautifully drawn car again. So we're saying it's going to the left. So that velocity initially is to the left, but the acceleration is in the positive direction, to the right. How can you possibly have an acceleration that opposes your direction of motion? Well, we do that all the time. In fact, that is the only way that we can slow down. The only way that you can slow down is to have an acceleration pointing in the opposite direction that you were going. It is like taking velocity away. Remember that an acceleration is a change in velocity. So it makes sense that this acceleration is positive because that velocity is negative, and we're sticking with that. Everything to the left is everything to the left is negative, and everything to the right is positive. All right, everybody. Hope you enjoyed this and had a lovely day. And yeah, goodbye. See you later.